Welcome back to the Deep Dive, where we take your source material, your reading stack, your research notes, your coding roadmaps, and turn it into immediate, actionable knowledge. Our goal is to give you that shortcut to competence.
We're here to synthesize that understanding so you can stop wrestling with documentation and, start actually solving problems, whether you're walking into a meeting or firing up your first Python script.
Today, we are undertaking a deep dive into what is arguably the single most important library in the Python data ecosystem. We're talking about Pandas.
Oh, absolutely.
Your source material calls it the essential, fast, powerful, flexible, and easy-to-use open-source tool for data analysis. It really is the workhorse.
It's the cornerstone for sure. And for anyone just starting or maybe prepping for that first big project, our mission today is pretty clear.
Right.
We need to unpack the fundamental concepts, specifically the series and the data frame, and arm you with the essential utility functions and manipulation techniques that let you go from raw data to insight fast.
Okay, so before we even get into the data structures themselves, you highlighted a prerequisite. It's something that often trips up beginners, and it's not about the data, it's about the package itself.
Exactly. Before any of this amazing stuff can happen, you have to remember Pandas is an external package. It's not built into Python.
So you have to install it first.
You have to install it, usually with Conda or pip, and then, and this is the crucial part, it has to be imported into every single script or notebook where you plan to use it.
And there's a convention for that, right?
There is. Most people, I'd say pretty much everyone, uses import pandas as PD. Once that simple step is done, then and only then can we start building on that foundation.
Okay, so let's get into that core architecture. If we're building the house of data analysis, we have to start with the foundational brick, the basic building block. The series.
The series is officially defined as a one-dimensional labeled array. But a better way to think of it is just a single column of data.
A single column.
Yeah, and it's incredibly flexible. It can hold any data type you throw at it. Integers, strings, floats, timestamps, you name it.
So that sounds a bit like a superpowered Python list, or maybe a NumPy array. But your material highlights one thing that makes it fundamentally different and way more powerful.
And that's the index.
The index.
That is the conceptual leap you have to make. The index is everything. It's the list of access labels, which you can think of as the row ID or the sample ID. A unique key for each piece of data.
I like the analogy you used, like an old-fashioned filing cabinet.
Exactly. The files inside the drawers are your data, your values. But the little labels on the front of each drawer, that's the index. It gives context and structure. Without that label, it's just, paper in a box.
That makes perfect sense. It's the context. So I know you can create a series from a few different things, like a NumPy owned array or a Python dictionary or just a plain list. What happens if I use a list and I don't give it any labels?
Pandas is smart enough to handle that. If you give it an underarray or a Python list without an explicit index, it just creates a default one for you.
Which would be what?
It'll just be a range of integers starting at 0. So 0, 1, 2, 3, and so on.
What's really fascinating here is this duality that makes the series so robust. It feels like two different tools built into one.
Precisely. We call it underarray-like and dict-like. It's underarray-like because it's fast. You can slice it, you can pass it to almost any NumPy function, and you get that raw computational power.
But the real analytical power, that comes from the dict-like side of things.
Yes, because the index acts like a dictionary key. This means you can get your value not just by its position, like the fifth item in a list, but by its label.
So if I have stock data indexed by date, I don't ask for item number 50.
No, you ask for the item labeled 2023-1026. It's so much more intuitive.
And this design, this duality, is what unlocks vectorized operations and, maybe most importantly, label alignment. Let's spend a second on that. Why is that such a huge time saver?
It completely changes how you think about doing calculations. Let's say you have two different series. One is the daily stock price for Apple, the other is for Microsoft.
Okay.
And you want to find the difference between them. You don't have to write code to make sure that Tuesday's price for Apple is being subtracted from Tuesday's price for Microsoft. Pandas does it for you. It uses the index labels, the dates, to automatically line up the right data points before it does the math.
So if my Apple data accidentally skipped a day, Pandas wouldn't just crash or subtract Wednesday from Tuesday.
Exactly. It would see the misalignment, and it would just insert a missing value placeholder. That is a massive, massive efficiency gain.
It saves you from writing all that boilerplate code just to match things up. And that series, that labeled column, is the building block for the main event.
Which brings us to the centerpiece, the data frame.
Yeah.
If the series is the column, the data frame is the whole table.
It's the whole spreadsheet.
It's the primary 2D data structure in Pandas, absolutely. It basically takes a bunch of series objects and lines them all up so they share the same index. That's what gives you your rows and columns.
The sources gave a really intuitive way to think about creating one, using a standard Python dictionary.
That's probably the easiest mental map to start with. Think of the dictionary key as the name of your column, the column header, and the dictionary value is just a list of the data points that will fill that column.
So you're defining the structure before you even create the table.
You are. It maps very cleanly.
All right, so we've got our data frame. Maybe we just loaded it from a CSV file with pd.readtscsv. Now, the moment that data is loaded, before you do anything else, you need to run a full diagnostic check.
We call this the data health check.
And this is where the Pandas utility toolkit is just a lifesaver. Can't analyze what you don't understand.
Right, it's like an instant x-ray of your data's anatomy, and there's an order to it.
Let's run through the essentials, the quickest checks first.
Start with size and shape. df.shape is non-negotiable. It instantly gives you a tuple, number of rows, comma, number of columns.
It's your first sanity check. Did I load 10,000 rows or just 10?
Exactly. Then df.size just tells you the total number of cells or elements in the whole thing.
And since we know the index is so important, you have to check the labels.
Oh, for sure. df.index will show you your row labels, and df.columns will show you the names of your column headers. Simple, but you have to do it.
But the next one, df.dtypes, seems absolutely critical.
It is paramount. This returns a series that lists the data type of each column. This is the check that immediately tells you if something is wrong.
How so?
Well, if you have a column that's supposed to be a number, like price or age, but dtypes tells you it's an object.
Which means it's a string.
Great. Then you know you've got bad data in there somewhere, maybe a comma or a dollar sign or some text that's messing things up.
I can see how that one command saves hours of debugging down the line. It's like seeing the smoke before the fire really starts.
Yeah.
Now, if you want to ditch the labels and just get the raw, fast numerical data, you can use df.values, right?
That's correct. It just rips out the NumPy array from underneath. It strips away all the pandas overhead and just gives you pure array performance, which can be useful for machine learning models or other high-speed math.
Okay, let's move from the quick attributes to the functions that give us a deeper profile, the utility methods.
This is where we get the summary. If you're working with a big data set, like the famous Titanic data set mentioned in the sources, it has almost 900 rows. You don't want to print the whole thing.
No, definitely not.
So df.head and df.tail are invaluable. They just show you the first 5 or the last 5 rows, so you can confirm everything loaded correctly and looks how you expect.
But the two real diagnostic heroes here are two specific functions.
Yes. The first is df.info. This might be the single most critical function you can run right after loading data.
What does it give you?
It prints a concise summary, the index, the number of columns, their names, their data types. But here's the most important part. It shows you the non-null counts.
That's the critical red flag, isn't it?
It is. If your data frame has 891 rows total, and you run info, and you see the age column only has 714 non-null entries.
You immediately know you have 177 missing values.
Instantly. You don't have to hunt for them. You know exactly where your data cleaning problems are.
That's a huge time saver. And the other one is df.describe.
df.describe is your instant statistical overview for any numerical columns. It gives you the mean, standard deviation, min, max, the quartiles, all in one simple table. It's a great way to spot outliers or weird distributions before you write any complex code.
That feels incredibly efficient. Now, before we leave diagnostics, the sources flagged a couple of small, practical, real-world details. First, the dependency for writing to Excel.
Yes, that's a classic welcome to the real-world moment. You can write to a CSV file easily, but if you want to use to Excel, you need to separately install another library called OpenPixel first.
Why is that?
The Python data ecosystem is all about interdependence. Pandas doesn't want to carry the weight for every possible file format, so it delegates. Knowing that dependency saves you from a really confusing error message later on.
And the second point, which I really appreciated for its honesty, was the footnote about trying to pull live data from that OpenAir Quality API and failing.
Yeah, that's a good reminder that data work isn't always clean code. Sometimes the hardest part isn't the Panda syntax, it's just getting the data in the first place.
Fighting with APIs, bad formats.
Exactly. The real struggle is often just getting the data to the door. Pandas helps you once it's inside.
Okay, so we've diagnosed the data. Now we need to start working with it, subsetting it, cleaning it. We can sort with sort values, but the real action is in selection, grabbing specific rows and columns.
This is the second major aha moment for anyone learning Pandas. You have to master the difference between df.ilock and df.lock.
They seem similar, but they're fundamentally different in how they think.
Totally different. Let's
Yeah.
start with ilock. ilock stands for index location. It uses strict, positional, zero-based integer indices. It's just like old-school array indexing. If you want the row that's physically in the third position in the table, you use ilock 2.
So it only cares about the physical position in memory, not the label. If I want the very first row, it's always ilock 0.
Always. Now, contrast that with df.lock. Lock is for selecting by label. It uses the actual names or strings that you assign to the rows and columns. So if your index is a list of customer names, you would use lock Jane Smith.
But here's the point of confusion I know people run into. If I just load a CSV file, Pandas gives me that default numerical index 0, 1, 2, 3. In that case, doesn't lock 2 do the exact same thing as ilock 2?
That is a great question, and it gets to the real power of lock. While they might seem to overlap with a default index, lock can do something ilock can't. Conditional selection. Boolean filtering.
So I use lock when I want to ask a question of the data itself.
Precisely. You don't care about the position, you care about the data's attributes. You use lock to find all the rows where, for example, the gender column is female, and the age column is greater than 35. You put that complex question right inside the lock brackets.
That makes the distinction crystal clear. ilock for position, lock for labels and logic. And we can use these for updating data too.
Yep. You use the same structure to assign new values. If you found the first 3 rows were bad data, you could use ilock 0.3 and just assign the value anonymous to a column to clean them all at once.
Now let's talk about another huge efficiency gain, creating new columns from existing ones. My first instinct, if I had to calculate, say, a tax rate across 100,000 rows, would be to write a Python for loop.
And that is the absolute instinct you have to unlearn when you start using Pandas.
Why? I mean, it would work.
It would work, but it would be incredibly slow. If you find yourself writing a for loop to iterate over rows in Pandas, you are fighting the library. It's built to avoid those loops by using the broadcast method.
So what's the practical difference in speed?
It can be orders of magnitude. A Python loop is slow. It executes one command at a time. Pandas operations are built on NumPy, which performs the calculation on the entire column, the entire series, all at once, using highly optimized C code under the hood.
So instead of a loop, I just write the formula once.
Just once. dftax equals dfprice 0.05, and Pandas applies it to all 100,000 rows almost instantly. You do not need a loop.
That is probably the single most important time saver for anyone moving from basic scripting to real data analysis.
It truly is. You have to embrace the vectorized operation.
Okay, let's move to the final essential step, combining different data sets. We almost never work with just one clean file.
No, data analysis is almost always about stitching different sources together, and Pandas gives you 2 main functions for this, pdd.concat and pd.merge.
Let's start with concatenation. What's its job?
pdd.concat is the general function for just combining things along an axis. Usually that means stacking data frames on top of each other, row-wise.
Which is like a SQL union.
It's conceptually identical to a SQL union. You take table A and you just stick table B right underneath it. It's perfect if both tables have the same columns.
And if they don't have the same columns?
It'll still work. It will just fill in the missing columns from either table with placeholder null values. It's for adding more rows of data. But when you need to link tables together based on a shared piece of information, you switch to pd.merge.
Right, so merge is for joining tables column-wise using a common ID, like a customer ID or a product's XU.
This is where we get into full-on relational database logic. And the most important parameter you need to know for merge is the how parameter. It tells Pandas what kind of join to perform.
The default is an inner join. What does that guarantee?
An inner join guarantees you only keep the intersection of the keys. So if a customer ID is in your sales table but not in your customer profile table, that sales record gets thrown out. It's the most restrictive join. It makes sure every row in the result has a full match from both tables.
But what if I want to keep all the information, even if there isn't a perfect match?
Then you'd use an outer join. An outer join takes the union of the keys, it keeps every single row from both tables, and just fills in the missing data with NaN where a match couldn't be found.
So that gives you the most complete picture of all your data.
It does. Then you have left and right. A left join keeps everything from the first or left data frame and only brings in matches from the right one. A right join does the opposite.
So if I have a master list of all my products on the left and a short list of recent sales on the right, a left join would show me every single product, even the ones that haven't sold.
Exactly. It's all about what question you're trying to answer.
Before we wrap up, you also mentioned how simple it is to work with text data.
Yeah, this is a great feature. If you have text columns like name in the Titanic dataset, all the string methods you already know from Python dash like .lower.contains or split can be applied directly to a Pandas series. You just add .ctr in front.
So you don't have to learn a whole new set of syntax.
Nope, your existing Python skills translate directly.
Okay, let's bring it all back together for someone listening. What are the key takeaways?
It really all comes back to structure. Pandas is built on this dynamic interplay between the 1D index series and the 2D tabular data frame. Understanding that structure is the key to control.
And to get that working control, you need to master two things right away. First, your instant diagnostic kit-shape D-types, and especially info, to understand your data's health.
Before you even touch it.
And second, mastering selection. Knowing that iLock is for physical position, and lock is for labels, and most importantly, for logical filtering.
And finally, never write that for loop. Embrace vectorized operations and understand the difference between stacking data with concat and relating data with merge. Those are your fundamental pieces of control.
Which brings us to our final provocative thought, building on that merge discussion. We covered the 4 standard joins, but there's a 5th, more radical option, the cross join.
Right. A cross join is different. It doesn't need a common key to work. Instead, it generates the massive Cartesian product from both tables.
What does that actually mean?
To give you a sense of scale, if you have a product table with 50 items and another table with 10 different pricing tiers, a cross join results in 500 rows. It pairs every single one of those 50 products with every single one of those 10 price tiers.
That sounds like a massive intentional duplication of data.
Yeah.
So when would a data scientist ever deliberately choose to create a data set where every row in the first table is paired with every single row in the second?
And that's the question we'll leave you with. What kind of complex comparative analysis, or maybe a simulation, requires that every possible combination of variables is exhaustively laid out? It's a niche tool, but a powerful one to mull over as you start your data exploration.
A great question to explore. We hope you feel far more prepared to tackle the fundamentals of Pandas and leverage its power for your next project. That's it for this deep dive.